We're going to go and get started here. And we're going to start with the mass spectrometry here. And so in your book, this is going to be called structural determination. There's, of course, much more you can do than just structural determination. But in an organic chemist mindset, spectroscopy is all about determining what you made and what its structure is. Anybody know why this would be important? Okay, did you know, for example, caraway, if you give the wrong chirality for caraway, you will kill someone?
Wow.
It's a poison. So that's actually pretty true for most medications and most compounds that are biologically active. If you give the wrong chirality, it either has no effect or has a completely different effect. Sometimes it's benign as having a different taste, but sometimes it's poisonous. Okay? And it actually turns something that's a benign flavor you normally eat into a toxin. Right? Now, having said this, there is a company, Prozac, right? Prozac is the one that people take and they feel better? Less stress? Okay. Yeah, I always have an issue where I'll say Zantac sometime, which is the stomach medicine, right? But Prozac, actually, they lost their patent on that. It was a $14 billion a year for about 15, almost 20 years. Okay, that company lost its patent. Anybody know why they lost their patent?
Did they put the wrong structure on it?
Yeah. So my advisor's actually the one that did the scientific council that proved that they actually patented the wrong structure. So the one that they patented was inactive. It didn't do anything. And then they did not patent the one that actually had activity. So they'd been making something that they didn't have the patent for, and somebody could have actually patented their drug. They're lucky that somebody thought that they just came up with a derivative and then sold it instead. Somebody could have patented it and then claimed patent infringements. Yeah. So, just amazingly stupid, right? Yeah. So one of the things I'm going to point out, whenever you use these structural determination methodologies, you need to layer them. It's very rare to be able to do a structural determination with a single methodology and be 100% accurate. Okay? You have to have very simple compounds to have that happen. And this is actually a major cause of problems out in the industry. Okay? Now, you may be wondering why these things are important still. Well, has anybody ever heard of an Intel? We're a dominant manufacturer of CPUs. That's half the CPUs. Actually, nowadays it's more like a third of the CPUs. They could not get the chemistry corporation supplying them with supplies to give them pure samples. They kept putting impurities in them and not detecting them in their methodology, which is the methodologies I'm going to be showing you. And that actually is what caused them to slip 2 generations in the CPU wars. They've missed their targets now twice. And so they are utterly behind all their competitors. Yeah. Lost hundreds of millions of dollars to billions of dollars a year. Yeah. Used to be the manufacturer. Okay, folks, so now that we understand that these have huge consequences, right? Literally life-altering death consequences, okay? Mass spectrometry, this can provide insight into the mass of a molecule and the fragments that would compose of it. So essentially what we do is the MS, which is mass spectrometry, actually concentrates on the masses of things. And then what we usually do is we have something in the beginning of it that goes ahead and breaks our molecules. Okay? Now, there's a variety of techniques. There are derivations of this, but we need to understand the base technique first, right? So how this works is you're going to inject a sample. Typically, you need to do this as a vapor because you want it to move around. Okay? And so you're going to inject it as a vapor into a vacuum. That's going to cause it to accelerate a bit. You're then going to put an accelerating plates on both sides of what is called an electron collector or electron beam. Okay? And what this does is your sample's going to go through. See how it has a tube through this first one? And it's a little round plate with a hole in it. Okay. And so your sample comes through as a gas. Whoosh, right? And then it's going to go through this beam of electrons. Beam of electrons is going to cause electrons to jump on things and give it a charge, right? Now, most things, when they get an extra electron, are not going to be stable anymore, right? And so what you'll see is it'll actually break. The vast majority of these compounds are actually going to break, okay? You don't actually have to have an electron beam here. There are many, 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 many different options. There's ones with flames. There's ones with like high energy light. There's all sorts of options, okay? But the overall idea is you're breaking stuff apart to give it charged fragments. Everybody okay with that? So you're making charged fragments. Typically what's going to happen is you're going to have positively charged fragments that come off. And this is going to then be attracted to this negative, what's called an accelerating plate. That's an electromagnet, okay? And then you have a positive back here that's pushing it forward, right? And so now we're accelerating our sample. Is everybody okay with that? We took our sample, broke it into fragments that are charged, and now we're accelerating our fragments, right? Okay, so this accelerates forward, and then what we do is we put a bend. Now, anything that's neutral is just going to keep going straight now, right? Hit the wall and get pumped off by the pump, okay? On this bend, we're going to put a magnet on it. It's an electromagnet. We can change the magnetic properties of this depending on the amount of electricity we put, right? Anybody ever seen electromagnets? No? Nobody knows what electromagnets are? Okay. They're magnets. Essentially, they're wire wrapped around a bunch of times. And depending on the amount of electricity you pass through it, you make it more magnetic. Like, you see those magnets that lift cars? Those are electromagnets. Okay? This is not that strong of a magnet. NMR, actually, it is that strong of a magnet. Those things are crazy powerful. But, yeah, this is not, you don't need that level. You're bending molecules paths, right? Yeah. So what we do here is we go ahead and just increase the magnetic properties of those, right? Okay. And so what ends up happening is as you dial that in, as you dial through the strength of that magnetic field, it's going to start causing these molecules to bend, right? Any molecule that's positively charged, that has a charge on it, is going to bend, right? If you have the correct magnetic field here, you're going to actually bend that, and it's going to get to the end here, which is the detector, which will detect something passing or colliding with it. Okay? Okay. Is everybody okay so far? All right. Fantastic. And so what does that bending actually depend on? Charge. So part of it's charge, right? Exactly. Charge and mass, right? So the more charged something is, the more it pulls towards the magnet, right? But the amount, how much it changes its trajectory is dependent on its mass, isn't it? For example, I'm pushing against the planet. Am I getting much progress done? Dang it. Not shifting much, is it? Oh, I could have lowered the temperature right now. Or increased it. I don't know which way we're pointing right now. But, so what we're looking at here is, this is actually what's called an M over Z. Okay? It's the ratio of mass to charge that gives us how much this bends. And so depending on the electricity flowing here, we're going to be having different mass versus charges that make it to the end to the detector. Okay? Now this detector here usually has a plate with a little hole in it, and that keeps anything that slides along the wall will bounce off and then go off to the pump. And that just gets expelled. Okay? Everybody okay with that so far? Okay. this is the overall how all MS works, mass spectroscopy. Okay? You may note that there's all sorts of MS techniques. There's a lot of stuff you can add to these things. You can put stuff before. You can put stuff after. Those are called things like GCMS. Okay? Remember our GCs we did? You can put one of those in front here. Right? We can have MS, where we literally just take this beam, we put it through another one, and then we can do that 4 times if we wanted. And that's quad. And then we can select like small mass differences, like the differences between protein fragments. Okay? Because you can filter them out real accurately, right? Yeah. So, lots of options here. But overall, everybody have that base idea of how this works? Fantastic. Understanding this is incredibly important. And actually, this is one of the most hireable skills you're going to get taught ever, period, in the college. Okay? There is a giant facility where they have only about half the staffing they need in Mount Juliet. Biggest one in the country. And they have about, I forget the exact number. It is in the hundreds. About 200 of these instruments running almost constantly. Yeah. So if we get a chance, I'll try to set up a tour or something. But this might be short timing. I just got a tour like last week. And they were like excited and wanted people to come. They hire basically anybody with like an organic chemistry level of classes. So biology, biochemistry, chemistry. Because they can't get enough chemists.
That's hilarious.
Yeah.
That's hilarious. Could I go over there? I'm a biology
Yes.
major.
Yeah.
What's this place
Yeah, they'll hire you.
That's hilarious.
Yeah, because, traditionally, like 20, 30 years ago, they would have only hired chemists,
No
but
way.
you can't do it now.
That's great.
Yeah, they can't hire 100 chemists. It's just not possible.
What's this place called?
Okay, so it was called environmental something or another, but it's been taken over by PACE. So it's PACE Analytics now. But if it doesn't come up, it's environmental ESC? Yeah. Environmental science something?
Center for Testing and Innovation.
Yeah. Well, PACE is a huge company. That's an international company. So this was actually started by somebody that actually has their child going here and is paid for that room over there, the lab over there, to be renovated. Really nice guy. And he sold it to PACE. And so now it's owned by PACE. But
Used to be a small business.
I wouldn't call it small, but yeah, a lot smaller than it is now.
Large business.
Yeah. It was only like 1 or 2 labs, now it's like a complex of 10 or 11. Yeah. So it's been scaled up a lot, but they're actually kind of cool people. We should talk about them sometime. Yeah. Cool guy, cool facility. Yeah. This is neat. If I can, I'm going to try to figure out some way to do a tour, but I don't know if I'm going to be able to set that up. Yeah. It's been a kind of crazy semester, right? But if you want to just do a tour, we could probably arrange 1 or 2 people to do a tour. Pretty easy. They were nice people. Okay, and so what you always get out of here is you get the relative abundance, what's showing up on your detector. Usually this is a count of things that are passing it. Okay, but it can be a little bit more complex than that sometimes. Now, down here on the x-axis, this is that m over z. Okay, what do you notice by m over z, mass over charge? If I had a 2 plus charge, then I could have a mass twice what it was before, and suddenly it would show in the same place, right? Okay. Okay, so vaporization. We can use very small samples. This is typically on the order of less than 1 microliter. Anybody tell me how small 1 microliter is?
Small.
Anybody use the pipettes? The micro pipettes? Do they usually go down to 1 microliter? No.
The glass one.
Yeah.
One.
Yeah. Yeah, you have to. The only ones we have is the syringes, probably. We might have a micropipette that goes down to the 0.1 microliter. They're pretty expensive, though. And they take a lot of calibration to be accurate, so usually most school labs don't have them. Do we have a micropipette or just the syringe
Micropipettes, I think. They're all plastic, though.
that goes down to 0.1? I wonder if it's accurate. Usually they end up not being accurate.
I mean, those ones are just like the school training ones. They're not the actually nice ones.
Yeah.
So
Oh no, they're actually nice ones.
really?
If they're the same micropipettes that are in the biochem lab,
Yeah.
yeah, those are, well, they're not the top of the end, but they're the, I don't have infinite money, but I want a good one.
Gotcha.
Yeah, yeah. They're actually the same thing you'd see in a business.
The upper middle class of micropipettes.
Yes, they definitely are. Yeah, they're the ones you'd typically see in a corporation. That's not a like biomedical burning money thing. Yeah. Okay. Pace Analytics has room with those in it. So. Yeah. Yeah. I mean. Yeah. They have hundreds of machines. They have an instrument in there that the resale value is over $100,000.
Yes.
Yeah. Well, $10 million is the cutoff. Okay, so this right here would be the injection into the spectrometer. You're going to take a liquid, you'll inject it, it's going to go into a gas. It's going to do that because it's under vacuum. You can actually set up systems where you heat it. There's a variety of different things you can do to get this into the vapor phase. Okay. Pace actually has a pretty cool system to save themselves time, where they actually absorb it onto an absorbent material and then heat it to release it, so that they can specifically target specific compounds. Once vaporized, these gaseous molecules drip through a beam of fast-moving electrons. This is the most common method because it doesn't accrue a lot of damage from running samples. Okay, that beam of electrons doesn't heat stuff up and burn things, and oh my goodness, now I have to clean that. Yeah, so by far and away the most common methodology. So this right here is going to be your electron beam. It's going to be what's referred to as ionizing radiation, right? Or it's an ionizing beam, okay? And what that means is it makes ions, right? And so what you'll see is it'll come off, an electron will come off, and it's going to knock that electron off. You'll leave behind your molecule that has a positive charge. What happens whenever you put positive charges on these molecules? They're always reacting and rearranging, right? And so what's going to end up happening here is you're actually going to get the most stable fragment with the positive charge coming off. That's going to break off. And then you'll get the other fragments that will be neutral. Typically it's 2 fragments in most cases, but you can get lots of fragments if these things are long enough and they have enough states they could be in. Okay? Keep in mind you can also get rearrangements, excuse me. So again, we're going to have the electron. It's going to get knocked off, and then gaseous species will have 1 fewer electron then. This is going to give us our positive charge. So the process of producing this molecular ion is called electron impact ionization. That's this beam process. Okay. All right, so if we have a charged species like M+, this can be guided into a detector through a curved tube. This is going to use a magnetic field then to bend the ion's path so that it makes it to the end detector. And we'll only select for that mass versus charge ratio. Okay. So the extent that a given ion's path is bent is going to depend on your strength of your magnetic field. It's going to again apply to the mass to charge ratio. This is the specific way you would normally say that. This is how you represent it, M over Z. Most spectrometrists, most spectroscopists actually just end up saying MZ or M to Z. Okay. The detector is going to be designed to keep track of the number of charged species that collide with it. The number is going to be translated into what's called a relative abundance of your ion, and this will be your relative abundance. So then we can compare these and say, hey, this one has more of that, than this one, right? Okay. And these transformations actually do a pretty dang good job. And so typically we can actually take this relative abundance and we can actually use it as a straight up, if this was twice the height of this one, you'd have twice that amount of species. Okay? All right. So this right here is actually the compound you're looking at. Again, the x-axis is going to be the mass spectrum. This can be interpreted as the mass of the ions detected. Of course, it's over the charge. But if you only have a +1 charge, then that's going to end up being just the mass, right? So the M plus is going to be the peak of a mass spectrum that's going to be taken to be the compound's molecular mass. So this right here, see how it hits 100? Okay. Now, your highest peak is used, the reason this is relative abundance, not abundance, right, is that you actually divide everything by this highest peak. And so you've normalized it to your highest peak. And so that's your relative abundance. That's what everything's relative to. Okay? That's 100%. All right. You need to be really, really careful about this, by the way. The reason that Intel got messed up is because they were miscalibrating this instrument, their supplier was, and it was their relative abundances were wrong. And so they were not reading peaks that were actually blowing way off the spectrum. They were over 100. So they were supplying gases that had impurities in them that were actually over 100% of what they're measuring. Which is just horrifically bad. Yeah. Like, what the hell you gotta produce when you have impurities there? More than what you measure. Okay. And so this right here is what's referred to as your base peak. This is the one that has the greatest abundance. This is the most stable fragment, if you will. This right here is M plus. Can you tell me what M plus would mean? Anybody know what the molecular weight of this would be? Okay. Well, if we put a positive charge on that, does that change the mass particularly? No, that would just be the difference of an electron, right? We normally call that 0. And so, if it's M plus, then that means it is the mass of our compound, isn't it? Yeah. Okay. Congratulations. Yeah. Now, it does not need to be the species that has the greatest relative abundance. It doesn't even need to be the species with the highest mass you're going to see. Okay? But it's usually within the top spot. So it's contesting for the top spot. Okay, let's talk about some rules for this. Now, remember, rules are more like the laws, right, of like a human society. They're things that help you out. They're not limitations that can never be broken at all in any case whatsoever. Okay? There are some, but in organic chemistry, that is somewhat rare. So a compound that contains an odd number of nitrogen atoms typically has an odd molecular mass. Why would that be? Okay, CH4, is that even or odd? Carbon is 12, right? 16, so that's even, isn't it? If you multiply that number, you're going to get even numbers, right? CH2s, they are even or odd? Even again, aren't they? And so those are your backbones for most compounds, right? You're going to end up with even numbers overall for most organic compounds. Okay? Oxygen, even or odd? Even. And so what is the one substance that typically shows up in organic compounds that's odd? The nitrogen. If you have two nitrogens, that's even, isn't it? If you have one nitrogen, that's going to end up being odd. Okay? And for the vast majority of organic compounds, those are the only things you'd see.
Why? It doesn't work
It's because the number of hydrogens on it.
Oh,
Yeah.
okay.
Would it depend on the number of hydrogens, or can it be positive?
So you'll still have the hydrogens on it, even though it's positive. Yeah. So when we're looking at these here, we'll see some fragments in just a second. Okay. So the compound containing even numbers of nitrogen atoms or no nitrogen atoms at all typically has an even molecular mass. You'll see this in this one right here, which is 86, of course. Okay. So let's go ahead and look at some compounds real quick. This is our compound we just looked at. And this is that fragment that's just M+. Okay? And you'll notice again, we're blasting these electrons off, and they're flying along a path. They don't have anything that they can really impact much, right? And so they don't really get to do all the reactions that you would normally associate. In many ways, you could actually think of these as sort of frozen in time. Okay? So they can, however, fragment. So this is then the different fragmentations that are going to happen. And so what we get is a breaking of the bond right here. And this would give us this positive fragment with the CH3 here coming off. That's that tip, right? Now notice that's neutral, so that doesn't get detected. That just flushes away. Okay? Okay. This would be it breaking at this bond right here. And notice again, we get right here our fragment. This one's going to end up being 57. Note again, I was talking about this for the evens, which is our main one we just freshly charged. Okay. Okay, so again, here we have a fragmentation, and we get 43. Is everybody okay with that so far? That's just the remaining mass of these. Yeah. And what you notice again is we don't have a base that's available. We can't do the reaction where we're going to have a base that will take these hydrogens. And so we can't get these next steps of the reactions we would normally do. Okay? Okay, so let's try this out real quick. Let's use the mass spectrum of the ethyl benzene that we provide to identify the M+ peak and the base peak. What's going to be the formula for the ion responsible for the base peak? Okay. So what is the base peak?
The tall one?
The tall one. Yeah. Yeah, it's what we base all the numbers on, right? We base the abundance on. Okay? And so that's our base peak right there, right? So it's one that's 100. Okay. Okay. And so what's going to be the one that the M+? This one won't be the M+. Oh, okay. Oh, okay, bottom down here? Yeah, this one up here? Yeah. Yeah, so this grouping right here is the slightly changed from M+, right? This would be things like gaining or losing hydrogens. And typically it's the one that has the highest peak in there. But you can always go ahead and look at your compound if you already know what your compound should be to the M+. If you don't know what your compound should be, then you would want to work through, could it gain a hydrogen, and get that number. Okay? Okay. So this right here is the number for our M+ right there. That's the 106. Okay. You will note that if we actually look at this right here, this is 5, 10, 15, 20, right? So there's 5. We go 1 up. That's the 6, isn't it? Okay. Notice there is one more, and that would be gaining a hydrogen, wouldn't it? Okay.
What's the unit for the mass?
AMU.
Okay, so an AMU.
Yeah. Atomic mass unit. This is how you typically go and express atomic mass units. I mean, technically, if you have a whole mole of it, I guess it's grams. But yeah. Okay, and so our base peak, if we look at our base peak again, is right here, right? And that one right there would be 90. Everybody comfortable with that? And then we go one up, and that's 91, isn't it? Okay. So we need to figure out what coming off of this would give us a 91. And so our whole molecule is 106, right? What would be the mass of a CH3? 15, you got it. And then a mass of a CH2? 14. Yeah. And so these are the sort of things you want to start taking off to figure this out. Okay. And so we look at our 106. We see we're down to 91 here. What's the difference between 106 and 91? 15. What's the only thing we could take off of that? That would be 15 mass. Yeah, our CH3. And so this is going to be our fragmentation, where we've broken off the CH3, right? Okay. We could have actually predicted that pretty easily, because what's the most stable location for a carbocation? Next to a benzene ring, right? Yeah. So it's leaving behind the most stable fragments it can, right? And that's what causes that to be the highest population right here. It's the same thing as we've always done, stability, right? Okay. Now, what would this be if we fragmented this one? What sort of difference in mass? That would be a 15 plus a 14, right? Okay, and that's a 29, isn't it? Okay. All right. Would we start fragmenting the benzene ring first? No, the benzene ring's very stable, right? So we would leave the benzene ring first, alone. Okay? Yeah. All right, so our M plus peak is going to be MZ86. There is usually a small peak next to it that's going to be higher mass. That's going to be 87. This is typically called the M plus 1 peak, because it's always the M, your mass, plus 1 mass unit, right? Okay. Can everybody see it okay? The really tiny one there? The tiny one. All right. Again, that's going to actually be where you have your molecular ion that contains the heavy isotopes in this case, which is the C13. If you look really closely, you're going to see that this is about a 100th. Can everybody sort of see that? That's because C13 is actually 1% of carbon, right? Yeah. So that's what we're getting, all these small peaks right here. See all the small peaks here? Okay. C13, but in this case C13s and some deuteriums. Very little deuterium. But we can also get any of the isotopes and their isotopic ratios. Okay? So for example, if we had nitrogen, we would get the isotopes for nitrogen, oxygen, get the isotopes for oxygen. You'll note we don't see things like the C14 here. You're not noticing the C14, but that's because the amount of C14 is so low you just aren't seeing it here. Okay? If we had a much more sensitive system, we could actually start seeing C14. Right? But we would need to blow this up a bunch because it's a very tiny peak. Okay. Is everybody getting the isotopes and how they play into this now? Okay. Very good. Very good. All right. This right here is your relative isotopic abundance, and that's the C13 that we're seeing. It's 1%. It's a pretty common one to see because 1%, while very small, is large enough to show up on these because we're in the 100 scale, aren't we? And so you'll be able to see things that are like 0.5% or so as tiny little peaks down here, right? Okay, if we go over here, we can see that technically we should see deuteriums as well. But look at that ratio. It's 100 times lower, isn't it? So we would be dividing by 10,000 times our height, right? So is the band there for a more isotopes being added to something? Sure. Is it something we're probably going to see? Mostly not. Okay. This right here is nitrogen, and that's nitrogen 15. There we have our oxygens. You'll notice that most of the most common organic compounds don't have a lot of isotopes. They're in significant quantities. And so carbon tends to be your big cause of those small bands. Okay. However, if you start adding things like chlorine and bromine, what you start seeing is chlorine has a 24% abundance of the 37Cl. That's why it has that 0.5, right? Number. And you start looking at bromine, and we see that that has a 49% of 81. So if we looked at a bromine spectrum, you'd actually see two peaks. They're about the same height. What would be the difference between those two peaks? A 2, right? Yeah. So we'd see two peaks, 2 apart. And they'd be almost the same heights. And that's a bromine isotope, isn't it? Okay. Okay. Anybody have any questions about those so far? Fantastic. Okay, so this is again the M+1 peak. And so you're going to get a small medium in almost all these cases where you have these organic molecules. This is why automatically I was always just going dink for the M+, because this one's always the M+1 for almost every organic molecule. Okay. These are going to be identified, the two peaks with the highest masses. That means furthest to the right on the spectrum. So this is the M+2 peak. These show up for things like chlorine and bromine. Everybody see it okay? Mm-hmm.
So sorry, the M plus is the most abundant one, so like for oxygen that would be 16. And then the
Yeah.
M plus one would be oxygen 17.
Yeah, I mean if you had enough of that to actually show up, yeah.
Okay.
Yeah. Yeah. So for like if it's just carbon alone, it'd be 12 and then 13, right?
Okay.
Yeah. This likely would not show up for oxygen. These are almost exclusively a carbon phenomenon.
But so whatever the tallest one is, that is always what would be on the periodic table.
Yes.
Okay.
Yeah. Because that's going to be the one with your most abundance. And you always see a real tight grouping. Okay? Okay. And it'll be the highest mass. Okay, here's the ones where we have a different isotope actually. And so these are the chlorines, those are the M+2s. And what you're going to see is, again, that ratio is going to be the isotopic ratio. So see, this is a 3 versus 1 ratio. This one being 24%, this being the 76%, right? This one here is for bromine. It's an M+2 again, because we have 2 extra mass units for that isotope. And that one's basically a 1-to-1 ratio, because it's a 49 versus 51% isotopic ratio. Okay, so let's go ahead and look at an example of this. So right here we actually see our M plus and our M+2. Can everybody see it okay? And that's for our bromine. See how it's just a little bit different. 51 versus 49%, right? Okay. What are these small ones? They're like a +1 to each of these, isn't it? Those are the M+1s for these. So that would be your carbon-13. Because you can have a both isotopes of bromine, and you can end up with one of the other isotopes of carbon on here, right? Okay. So you can have multiple isotopes. It's not like we're making these on purpose. That's just how molecules are, right? Atoms. You have a certain abundance of them. And so when you have a pretty even split here, you actually start seeing the M+1s as well. Okay? Okay. Anybody have any questions about that so far? All right. Fantastic. All right. So let's go ahead and look at some of these where we have some fragments coming off. Okay, so notice that here you get a really nice M, and then you get an M+2, right? Looks pretty good. And then over here, we get one that is how much sort of separated. What's the mass of bromine real quick? 79.9, okay. Okay, so right here, again, these are one fragments right here that are going to have bromine, and that gives you a separation of 2, and we know they have bromine because they have separations of 2 everywhere, right? This one as well. They're always some value of M plus 2. So those ones have to have bromine, don't they? How about this stuff over here where you're not getting 2 bands that are about the same height? If it had bromine, we'd have to have 2 bands about the same height, wouldn't we? Okay, so these have to not have bromine on them, don't they? Okay. And so we can actually figure out what those fragments would be based on the fact that we've had to have lost bromine. Okay, we have to have some sort of rearrangement that would lose us bromine. All right. Okay. So does the compound that's produced the spectrum shown here contain chloride or bromine? And why? Why would you say such a thing? Okay. So see, you have different masses here, right? Okay. And then you look at the ratios, right? And what sort of ratio are we looking at? 1 to 3, and so that means what? Chlorine. Got it. Why is it chlorine? Yeah, the ratio matches up with chlorine, doesn't it? So the ratio matches up with the natural abundance of chlorine. We have an M plus 2. That means we had to have something. The isotopes are 2 difference. And so this has to be the chlorine, doesn't it? Okay. Okay. Did I lose anybody in that? Mm-hmm.
So, I'm sorry, just on like the example before the one we just did with
Mm-hmm.
bromo, why, so like this is like what it's dissociating into after it's being hit with the positive charge? That's why there's like things
Yes.
that are much smaller masses
Yes.
than what the M plus and the M plus 2 is?
Mm-hmm.
Okay.
So what's happening is we have this positive charge on here, okay? And this one right here is going to be it breaking down to whatever's most stable, okay? So it's going to just be the most stable possible fragment we can get with a carbocation, with a positive charge on it, okay? This right here is going to be the parts of it that didn't actually break down yet, okay? Eventually they would, yes. Eventually everything's going to this right here. You gotta remember, these things are being shot out at hypersonic speeds. Okay, we accelerated them to very fast speeds. So the whole thing doesn't have a chance to break down yet. And then what we would get here is these are going to be different fragments that will depend on the stabilities, right? So the higher the fragment size, the more stable that compound is. So for example, this one right here would be the second most stable, wouldn't it? And it's actually fairly stable. This one right here contains bromine in it, and we know that because it's 2 almost equal peaks, right? If we had chlorine, we'd have 1 peak that's 3 to 1, right? Okay. Okay. That making more sense?
Yeah, so those 2 peaks would just be like losing one of the methyl groups on the opposite side of the bromo?
Yeah.
Okay.
This would likely be losing. So this one right here has a rearrangement where we've lost bromine as well. Let me see. It'd be 80 down. So that's probably just losing the bromine period. And then this is losing some sort of methyl or something. Whatever the difference there is. I'd have to calculate. Yeah. And yeah, this would be something like losing a methyl. So you have a carbocation right there. That making sense?
Yes.
Now, note that carbocation here, this right here is withdrawing electron density, right? So this one ends up a bit less stable than this one. These are probably interrelated, by the way. They're probably losing the same carbon structure, just you've lost the bromine with one during a rearrangement. Whenever you have bromines, it's pretty common because they're pretty leaving groups, right? Yeah. Did that make sense? Okay. Did I answer the question? I feel like we covered more ground there then. Okay. All right, so let's look a little bit deeper. Let's go ahead and estimate the number of carbons from an M+1 peak. And so what do you notice? Okay, so let's think about this, right? My likelihood of flipping a heads when I flip once is what? 50%. My likelihood of flipping it if I flip twice, getting one heads, is what?
50%.
No, if I do it twice, it's 50.
Okay.
Yeah, yeah. So I have a 25% of not getting heads at all, right? And then a 75% chance of getting some heads at some point. Okay? Is that making sense so far? And that's how probability works, right? And so when I'm looking at isotopes, what I'm looking at is I have a probability every carbon, it's about 1%, right, of that being an isotope. That's the C13, don't I? Okay? And I have a 99% probability of it being the C12. Is everybody okay with that? This is why you don't normally see double isotopes, because to get double isotopes, I'd have to do a 1% and another 1%, right? And so at that point, I'm 1 in 10,000. Okay? So if I have more carbons, then what happens to my chances of striking an isotope, to get an isotope? It increases, doesn't it? Just like if I flip my coin more times, I have a higher chance to eventually get a heads, right? By the way, do not do, if you guys have to do any stats or probability, like actual tests, where you do the action to see how it models out, do not come and talk to me. Okay? You know that doors rearranging for the, okay, you know the Price is Right, the 3 doors?
Oh, yeah.
And you're supposed to find, if you make a choice, they close one of the doors, and then you change your choice, you have a higher chance of striking it. Somebody brought that to me. We did it 100 times. I lost 99.
Oh,
Their data was so messed up. Yeah, I am like notoriously bad luck. So do not do the stats thing with me. Your data will look awful. All right. So here, what we're looking at is we would have a 1% chance each of these carbons to get a C13, right? So what ends up happening is the more carbons you have, the higher this peak, the +1, is. So this M+1 will actually increase in relative abundance versus the M+ peak. Is that making sense so far? So if you take these ratios, you can actually figure out the number of carbons that's in your compound based on that isotope. Okay. Everybody good with that? Okay. Now technically you can kind of get that from doing the fragments, but this is so much faster. So I highly recommend understanding this and using this whenever you assign things. By the way, you will be assigning stuff, right? So lots of homework. Now, your ratio of M+1 peak intensity divided by the M+ peak intensity is actually going to give you the number of carbon atoms. It's actually just that simple. Okay? And so what you'll see here is if we take the intensity of our M+, the intensity of our M+1 over that, we're going to get the number of carbon atoms. Okay. So let's estimate the number of carbon atoms in the compound that produces the following mass spectrum. So the first thing we would have to do is we'd have to go over here and we'd have to figure out how high these peaks are. In this case, it's been made a little bit easier because this one's 100, right? Okay. How do we get the height for this one? Okay. So what we want to do here is if you're trying to measure something like this, take a straight edge, usually a piece of paper works nicely, okay? And then you're going to want to get it even. You'll use that to trace across, and you'll mark a line here. Okay? And then you would go ahead and just go through and do halves, half, half. And keep halving between each line you draw until you get enough markings that you can actually read it. Did everybody see how I did that? Okay. That's actually how you figure out from one of these charts where this is. Right? If you have a ruler works better. But you don't always have a ruler with you, right? Okay, so we go ahead and figure this out. About what would this be, by the way? Yeah, somewhere 8-ish, right? Yeah. Under 10. Yeah, a bit under 10. Okay, and so we're going to go ahead and get our heights. We have here a 7 over 100%, because those are the intensity of our peaks, right? Everybody have that okay? Okay. This is then going to be times 100% over 1.1%. Anybody tell me where I got the 1.1%? Yeah, that's the isotopic abundance, right? So what are my isotopic abundances? That's what I plug in here. Okay. Okay, what we see is that this is going to be 6.4 that comes out. And so our estimated number of carbons is going to end up being 6. We just round it to whatever number is closest. Okay.
You could round up if need be.
You can round up if need be, right? Though it's keep in mind that this is not going to be perfect. It's an estimate. So if you start seeing other evidence piling against that roundup, round down. Okay. And overall, because of the isotopes, you do tend to end up with more situations where it's going to be rounding down. So, okay, so we're going to assign the rules for doing this. The sort of quick flow chart, if you will, is going to be assigning the M plus peak. If the MZ value of the M plus peak is not already given, try to assign it as follows. So at the high mass end of the spectrum, that's the far right end of the spectrum. I guess that's this far right for you all. Okay. Look for the two major peaks that are separated by the +1 if it's only carbons, 2 if it's chlorines or bromines that might be in there, in their MZ values. If you can locate that pattern, then the lower of the two MZ values is likely the M plus peak, and the higher one is the M plus 2 peak. Okay? If there's no M plus peak that's apparent, then you're going to find the two highest mass peaks whose MZ values differ by 1 AMU. If the lower mass peak is significantly more intense, that is probably your M plus peak. If its higher mass peak is the M plus 1 peak. Okay, did I lose anybody in these so far? Essentially find your M plus peak. If you have a +2, then it's the chlorine bromine. And you have that one. Okay. If you have only a +1, it's only carbons, right? Yeah. And yeah. All right, you're next going to record the number of carbon atoms. If the number of carbon atoms is not given to you, you're going to estimate the number by taking the M plus ratio, abundance, and the M plus 1 peaks. You're going to use the equation 15.3, which is the one we had just used before. Keep in mind, you may have to actually look up the isotopic abundance. Okay? By the way, if you were to plug in 100 over 1, that previous one wouldn't have changed significantly, right? Yeah. Mm-hmm.
So sorry, was that 1.1%? Is that a constant, or is that going to change every time you use it?
It will only change if you go outside the solar system. Yeah. So, full answer. Hey, you know there was an extrasolar object that's found on Earth. Did you guys know that? Huh? No, not China. So there was, this is actually a crazy story. So there's a Harvard scientist that had been a laughingstock of his community because he believed an extrasolar object impacted the Earth quite a while ago, and it was in records that they had seen this object impact in the ocean in these coordinates. And he believed it was extrasolar because of the trajectories. And so he got a crypto billionaire to fund a expedition where they then dredged the seabed to look for fragments of this object. And so they brought up fragments of what they believed is this object. They then tested this object. It has a different isotopic ratio than this solar system. And so it is very likely an extrasolar object that came into our solar system and then impacted Earth.
When?
I don't remember. It was... I don't remember when it impacted. No, it doesn't kill the dinosaurs. It wasn't a very big one.
Did you know about the asteroid that's possibly going to hit Earth in 2032?
No, I didn't look it up.
It's
Like a 180 chance.
yeah, it's super low chance, and also a super low chance if it does impact Earth that it would actually impact places that are populated.
Mm-hmm.
But it's large enough that it wouldn't be burned up in our atmosphere, and it's getting
Cool.
fairly close.
Cool.
So
Yeah.
it's a kind of cool story. Yeah,
Yeah.
exactly.
That's
We're
happened
not
like...
gonna be alive then, so.
There's been a couple times in my lifetime that we've had some pretty close misses. And a couple of those were actually planet killers.
Ooh.
So
This one, I don't think is one.
I'm not too worried about the asteroid stuff, though.
Yeah,
Like, humans are adaptable enough that we'll survive it.
exactly.
Yeah.
It'll just be rough for a little bit if it does impact like a major city or something.
Yeah. Unless it impacts directly on me, I'll be okay.
Yeah.
All right.
What?
So the third step here is going to be we determine if the molecule contains any heteroatoms. What are heteroatoms again? Yeah, not carbon. Yeah, so we're going to determine, does it have nitrogens, oxygens, that sort of thing. Bromine, chlorine, of course. Does the nitrogen rule suggest the presence of nitrogen atoms? Did we have an odd number starting that off? And did we get even numbers when we lost CH3s? Okay. If an M plus 2 peak is present, do the relative intensities indicate we might have a bromine or chlorine? You could get an M plus 2 peak that's a 1% intensity, right? And then would that be a bromine or chlorine? No. Bromine and chlorine's chlorine's going to be like a 24% intensity, right? Bromine's going to be like 50-50, 49% versus the M plus. So these will be significantly larger peaks, right? It is possible to get something like an M plus 2, though, without a bromine or chlorine. Compute the remaining mass. So we go ahead and subtract the masses of the C12 atoms that you determined in step 2, and the masses of the heteroatoms you determined in step 3 from your molecular mass. You determine whether the hydrogen atoms can account for your remaining mass. If so, then you have a complete molecular formula that could be feasible. Okay, and everybody remembers your formulas for hydrogen atoms typically, right? Okay, there's typically something like 2n plus 2, right? Okay, or it could be 2n, or it could be 2n minus 2. But it's not these huge differences. Okay? If you're missing 20 mass units, there's something else. You missed an atom. Okay? It's not hydrogens. If the number of hydrogen atoms is unreasonably high, then we're going to consider adding another non-hydrogen atom, such as a carbon, an oxygen, a fluorine to that formula. You're then going to go back into step 5 and do it again to see if you can account for the remaining missing mass with hydrogen atoms. Okay? The big one is too high. So what's the maximum hydrogen atoms you can have per carbon?
4.
Well, really 3.
Really 3, right? And really 3 on the ends, right? Yeah. So if you have 3 times your number of carbon atoms, hydrogens, and you're still missing mass, that's definitely not hydrogen. Okay? That gives you a real clear indication. And really, 2n plus 2 2N plus 4, those typically tend to be your sort of soft cutoffs. You kind of know if you're somewhere in that region that you probably need to start looking somewhere else, okay? Yeah. But typically 3N gives you plenty. You don't have so many carbons that that's going to stack up that much. Right. Okay. So this right here, we're going to determine the molecular formula for this. So right here we have an unknown. And so we have right here a 30% abundance. This is a 2.4% abundance. What would be the first step for this? So what was that first step? Were we given the M plus? Were we told the M plus? No, we have to figure that out, don't we? Yeah. So what would be our M plus? Yeah, this one that has the 30% abundance label on it, right? If we look down here, this is 129. Can everybody see it okay? And then the M plus 1 is 130, right? Okay. Okay, and so that is our M plus. What's the mass of our molecule for this? The whole thing? And it's the 129, right? The 130 would be with the carbon 13 isotope, right? We don't normally count carbon 13s, okay? And so 129 is that top line number we're going to have to keep track of, and now we're going to have to account for it, okay? Think of it a bit like your taxes, right? Or your bank account. 129 is that top line number. You can subtract things from it and fill your bank account and transactions and buy all the stuff you want, right? But you can't go below it, okay? We need to account for every dime, right? So 129 is what you should be writing at the top, and then you're going to be justifying and building a case of how you're going to use that mass, right? What does that mass go towards? Okay. Okay, so the next step that's going to help you out is you figure out how many carbon atoms you probably have. How do you do that? Yeah. Okay, so let's go ahead and do it. So we take which percentage on top first? 2.4 on top, and then we do what? 30% underneath. Yeah, yeah. So 30% underneath. In this case, this isn't our highest peak. Yeah, yeah. In the previous case, that was our highest peak. Okay. Then the next one is going to be the isotopic ratios, right? Okay. And so what's the number we put on top? 100. And then what do we put on bottom? 1.1, exactly. Now, that one is typically, frankly speaking, it's very unlikely you're going to have any problems if you round. Okay? Most people I've seen do this just take 100 divided by 1, which is 100, right? And then they don't have to do extra work. Okay? But, yes, I'm trying to teach you correctly, so thank you. Okay, and so we get 7.3 from that, right? And so how many carbons do you think you have to account for here? Yeah, we probably need to account for 7 carbons, right? Okay, and so for the next step, we're going to look at the nitrogen rule. So do we have odd numbers that came up for this M? We did, didn't we? Yeah, this one's an odd number, isn't it? We had 129. Okay, so what would give us odd numbers typically? One or odd numbers of nitrogen, right? So we have an odd number of nitrogen. Okay, one is likely. I mean, most things don't have more than one, but an odd number of nitrogens. Okay, you can't have more than you could have 3 nitrogens, right? We could have 5 nitrogens. Anybody ever seen something like hemoglobin? The heme group? No? DNA? The bases in DNA? Those have odd numbers of nitrogens, most of them. More than one nitrogen, right? Okay. Okay. So we have an odd number of nitrogens. Do we have an N plus 2? No, so we don't have to worry about bromine or chlorine, do we? Yeah, none of that junk. Okay, so the next thing we're going to do is we're going to take the things we know so far, and we're going to go ahead and try to account for our mass, which we also know, right? So how many carbons did we think we have? 7, and so the mass of those carbons would be what? 84, exactly. 12 times 7, right? And so we're then going to subtract that from our total, which is 129, right? That would give us a 45. Now, we also know that we have an odd number of nitrogens very likely, right? So let's go ahead and use that now. An odd number of nitrogens, we can go ahead and start at 1, right? So we go ahead and subtract off the mass of our nitrogens. Now, we could start one by one. We could go the other way, which was what we would take is we would go 3 nitrogens. So how much mass did we have remaining? 45, right? Okay. Okay, so one of the easier ways we could do this, and this is the ambiguity I was talking about. Remember I said that you don't want to just take one method and go, I have 100% got this. I could not be possibly wrong. Okay? It's because there is ambiguity in any one spectroscopic method. You can use other spectroscopic methods to go ahead and patch that ambiguity to give you a surety. Okay? Okay, so we're going to assume here that we're going to go ahead and try to finish this up as quickly as possible and go, okay, what would happen if we had 3 nitrogens, which is also an odd number? What would that be? It would be 14 times 3, right? It'd be 42. Okay. That actually is less than the mass we have remaining, isn't it? 45. Okay. And so you could actually fulfill this next rule by saying I have 3 hydrogens. That would be the remaining mass, right? 3. And then I have 3 nitrogens, 7 carbons. Does that seem like a molecule you could write, though, very easily? No, that's going to be a very strange-looking molecule, right? That'll be a lot of double bonds, right? Yeah, lots and lots and lots of double bonds. You're going to have to only use 3 hydrogens in the whole thing. That doesn't seem like something you're going to be able to figure out, okay? So we got rid of that one, okay? We're not going to try that one. It's a little bit difficult to write out. I don't think we could actually write a structure that makes sense, right? Because remember, we have to make the noble-like configurations for everything. We have to follow all those Lewis structure rules, right? So that's probably not going to be possible. Okay, so we back off the 3. We can't go any more because we don't have that mass, do we? Can't pay for the extra nitrogens. So we only have 1 nitrogen. We subtract the 45 by 14, right? So that would be 31 hydrogen atoms now, right? Okay. So how many hydrogen atoms can I fit into this?
Around 20-ish.
Yeah, so usually we're going to be somewhere in like the 3n plus 2, or, you know, my nitrogen could add an extra 1, right? Okay. And so we had how many carbons again? 7. 3 times 7 is 21. And so an extra plus, let's call it 3. Okay? 24. That doesn't take care of the 31, does it? Okay. So, what do we have to do? Well, we have an extra heteroatom. We have to go ahead and put something like an oxygen or fluorine that's going to account for that extra mass. Okay? And so, valid formulas that would fulfill this so far would be a C7, right? Okay. Then we have an N. And then we could have an oxygen in it, or we could have a fluorine. Okay? And then what we would have is if we have C7NO, then that would be 15 hydrogens, right? If we have C7NF, that would be 12 hydrogens that we'd have to use to fill in the rest of that mass. Okay? And up to what the rules I've taught you are, and up to what we've done so far, we don't have really any way to differentiate those. Okay? So far for this problem. Yeah, there are rules and things we can do with the rest of the spectra. Notice we're only using this little part of the spectra so far, right? Yeah. So there are stuff we can do with the rest of the spectra to help us figure that out. Okay. But so far, that's as far as we can go. Okay. We just needed to get all the rules encapsulated, right? Actually use them. Okay, so go ahead and try this one out. You're going to sit there with your piece of paper and information. Oh, am I already over time? Yeah, okay. Okay, this is what you're going to be thinking about all weekend as you study for the exam, right? And get ready. You'll be obsessed with it. What compound could this be? Oh my goodness. Okay. Did anybody send me an email to remind me to... Okay. If somebody gets a chance, could you send me an email to remind me, look at the problems for 24 and take off the problems that are the spectroscopy. Okay, thank you very much.
Your email's on the syllabus, or?
Yep, it's J. Clausen, Jklaa. It usually auto-completes by the time you get the KLA. Yeah. Oh, thank you, bud. You have a good one.